Okay, and we're recording. Okay, so let's see. Here's where we were last time, or where we left off. So we're going to talk about what I'm going to call deformations. So what this is I want to address the question of what happens if in an equation, for example, everywhere you see a z, if you replace that with 2z. So, for example, you look at this equation right here. Here's an equation. And now notice, as indicated above, where there was previously a z, I replace it with 2z. Right? Now, just to be clear, when I say replace, I don't mean typographically. I don't mean just stick a 2 in front of it, right? If I just put a 2 in front of it right there, that would suggest it would be 2z squared, and that is not what I mean. What I mean is that wherever there is a z, and whatever subsequently happened to that z should now happen to 2z, right? So notice the parentheses, right? So the parentheses are like this. So that 2 does get squared, as I have it in here. Okay, so that's what I mean by a replacing. Okay, so notice, of course, what that does is it turns one equation into a different equation. And here's the big question. If I know what the blue surface looks like, keeping in mind what this replacement was, what does that tell me about what the orange surface looks like? Right? So, said differently, to the algebraic process of replacing z with 2z, what is the corresponding and resulting geometric effect? Right? So we make an algebraic change. I want to understand the geometric effect. All right. So just as a for example, you'll recognize this blue equation, of course. That's obviously just saying rho equals 13. So that's the equation of a sphere, nothing to it. Easy surface. And I can fairly effortlessly note that this point right here, 3, 4, 12, works in that equation. By the way, it's what we call a Pythagorean quadruple. Y'all may have heard of Pythagorean triples, relatively rare sets of integers where the numbers work out real nice. Anyway, okay. Now let's just belabor the obvious here for a quick moment. Because this orange equation is a different equation, that point doesn't work in the new equation. Well, of course it doesn't. What a silly thing to say, right? I mean, in the original equation, that 12 was the z that got squared. In some sense, to make the arithmetic work out, that 12 needs to get squared. If I plug in 12 for z in the second equation, the first thing that happens to the 12 is it gets multiplied by 2. Then it's 24 that gets squared. I've fiddled with the arithmetic. Of course it doesn't work out the same. This is all silly nonsense. Okay. All right, so the reason I go down that road of thinking about the silly nonsense is that it kind of suggests a fix in a way. Namely, let's think about this point right here, 3, 4, 6, right? And the point is, this 6 right here, yeah, that goes in for the z, which then gets multiplied by 2 and becomes the 12 that needed to get squared, right? So said differently, because I knew there was going to be a multiplication by 2 that happened as a result of the replacement, I needed to kind of prepare for that. I needed to account for that by dividing the z-coordinate of the point by 2. Yeah? Plausible? Okay. All right, so what we have is an answer then, in fact. And let me get rid of all of the rest of this stuff. The effect of this replacement, if you replace every z with 2z, the punchline is that all of the z-coordinates kind of get cut in half, or said differently, we are vertically squishing our surface. That's the resulting effect on the surface. So this is a way that I like to think about certain kinds of things in math, that there's a connection between algebra and geometry. Algebraically, I do a certain replacement. Geometrically, there's a certain effect. Okay. All right. So as a broad rule, this holds. Whatever you do to a variable in an equation, in some sense, the opposite is what happens to the set of solutions to that equation. So, okay, so this is a very broadly applicable tool, and here's a quickie example. We're not going to spend a whole bunch of time on this, but that's obviously the unit sphere. No problem there. I can take that unit sphere, I can do certain changes to it. I can replace every x with x over a. I can replace every y with y over b. I can replace every z with z over c. Right? So I just did some algebraic tweaks to my equation. And what can I say about my resulting surface? Well, my resulting surface, in some sense, the exact opposite of the algebraic tweaks is going to happen to the set of solutions. So because I replaced all the x's with x over a, that's going to stretch outward in the x direction by a factor of a. And by the way, easy, I'll say, loose confirmation. You can think about specific points. So in some sense, this point 1, 0, 0, right? 1, 0, 0 makes that equation work. And well, having stretched it out, this point now a 0, 0 works there. Everybody on board? All right, so it's a nice little tool for your toolbox, nice point of view to keep in mind. I'm going to let y'all read these last two examples here. They're pretty straightforward. It's pretty analogous to what we just saw. And nice punchline, y'all will recall that we previously called this a paraboloid. It's a result of a rotation, so you might say it has circular cross-sections horizontally. Well, when you stretch it out, like I have done here, big surprise, we call this an elliptical paraboloid, because that circle, that had been horizontal circular cross-sections, gets stretched out to become ellipses. So thus the name. And then likewise for this next one, what we have down here, you can see it derives obviously from the hyperboloid on the left. This now we call an elliptical hyperboloid. Okay, all right. Enough of that. Okay, moving on to section 2.3. Oh, you're going to notice we're skipping section 2.2. Not on the content syllabus. You're not responsible for anything in 2.2. This makes me a little sad because the material in 2.2 is really, really important from a mathematician's standpoint. A lot of what we're going to do in this class is going to involve limits. If you think about it, flash back to single variable calculus, right? Every derivative you ever wrote down is defined with a limit. Every integral that you ever wrote down is defined with a Riemann sum, the punchline of which is that it is a limit. So limits are bonkers important in formalizing and being precise about what exactly do we mean by various calculus expressions. Right? And so ditto in multivariable, same story, and so it kind of hurts mathematically that we can't spend time talking about that. But it is it's formality, it's abstraction, it's rigor, and it's not really quite what this course is about. So again, makes me a little sad, probably makes you all happy, I understand, right? But anyway, we're not doing 2.2 at all. Okay, so moving on, 2.3, we talk about the derivative. This is actually a little bit premature. It turns out there's actually lots of kinds of derivatives. And the derivative is something we'll get to later, probably not even today quite. So I want you all to know this going in. There are multiple, something like 4 or 5, depending on how you count, different concepts in multivariable calculus that are of a sort kind of derivatives in a reasonable sense. And whenever you have a situation where you have a bunch of things that all go by similar names, you have a responsibility to make sure that that makes sense in some way, right? So what is it that suggests that all of these different multivariable calculus concepts should all be called derivatives? Why? What is it about? What do they all have in common? And the answer is all of the derivatives that we're going to talk about in their different ways relate input changes to output changes. This is a nice, pithy little broad stroke unifying feature of all of the different kinds of derivatives. So it turns out there's various different extremely useful ways to relate input changes to output changes, and thus the various different derivatives. Okay, now I'm going to start with partial derivatives, and not really because I want to. I'm going to start with partial derivatives for what I'm going to call logistical reasons. Pedagogically, logistic. I mean, the book does it this way, as do most multivariable books, by the way. And that it doesn't mean that I have to, but it means that I pay a price if I don't, and I don't think the price is worth it. So anyway, the reason that I'm kind of griping about this is because what I do think is important is this down here. I don't want you all to think that I'm starting with partial derivatives because they are the fundamental point of view on differentiation. They're not. They're easy to write down. People like them for that reason, but deep down, fundamentally, how should you think about derivatives? Not this. So I just want to give you that disclaimer. So I'm not saying you shouldn't understand. Obviously, I want you to understand everything that we're about to do. I'm just saying don't hang your hat. Don't set this as your cornerstone in your construction of your understanding of derivatives. This is not the cornerstone. This is a important tool, but we're going to see something much better. Okay, that said, here's how you do partial derivatives. Not that much to it. You have a function with a bunch of variables. Just hold most of them constant. Right? If you have 3 variables, for example, just decide for yourself, right? Free country and all that. I'm going to choose to view 2 of those 3 variables as constants. And so even though the function came to you with 3 variables, for practical purposes, at least for the purposes of this exercise, we're going to kind of treat it as actually only having 1 variable. So we're going to interpret then a multivariable function as a single variable function. And once you have a single variable function, then you just take the regular good old Math 111L derivative, Calc 1, all the usual. So it's pretty easy to define a partial derivative. I'll show you an example momentarily, but real quick, here's the notation. Y'all will kind of recognize that notation. Actually, these are kind of very, very similar, aren't they? Let's circle both of these. So you'll recognize that. It looks a lot like Leibniz notation for the regular derivative. An important clarification, though, this symbol right here is not a D. Cannot emphasize that enough. You really can't put a D there. If you put a D there, then you're stating completely incorrectly that you're taking a derivative of a single variable function, right? And you're not. So that's really wrong. Make sure not to do that. And I recognize, by the way, that that's annoying because this little symbol right here, right, that symbol might be a symbol that you haven't written before, and it might seem weird. You kind of have to develop a little bit of new muscle memory, and here's what I did when I was y'all's age. I actually spent about 5 or 10 minutes just kind of practicing, and I just sat here and did this for a while until I got good at it. And, some people, by the way, like to swirl sort of inward instead of, I'm an outside swirler. But suit yourself, right? But you got to make these silly little decisions so that you can be fluid with it. Also, very important. This is also not the Greek letter delta. Again, not optional, not okay, right? That delta means something else. So you can't do that either. So this literally is, you gotta just get used to making a new symbol. Yeah.
What's the name for that, and how would you say the degree expression?
Yeah. Good question. So this I think I would just call this the partial symbol. I wish it had a more streamlined kind of name, but I would just call it the partial symbol. And this I would pronounce as partial of f with respect to xi. Or if you want to be real efficient with it, some people say partial f, partial xi. Something like that. Yeah. Good. Okay, there is this other notation you'll notice over here. This does not look like Leibniz notation. This is kind of vaguely suggestive, perhaps, of the Newton notation, namely the prime, right? F prime. That prime was the Newton's notation. We can't use prime though because we've got to indicate which variable are we viewing still as a variable, and thus are we taking the derivative with respect to, right? And so we just do that as a subscript. It's just a notational thing. Reasonable option. There are some circumstances, just so you know, where this is actually fantastically convenient. And there are other situations where this is better for whatever reason. So either is fine, and you're going to notice that I'll gravitate toward one in certain contexts and the other in other contexts. And, you'll get the hang of it. Okay, so let's do one. Look at this monster. It's a product of three factors. One of them is a composition that has a product of inside of it, and oh my gosh, that's going to be hard, right? We're going to have product rule and chain rule and product rule again, and I've got to remember how cotangent works, and yikes, that looks hard, right? Good news, super easy. This is a really easy derivative to compute because, very importantly, recall, taking a partial with respect to y. That means that even though there's three variables in there, x, y, and z, only y, for the purposes of this calculation, only y is to be thought of as being a variable. The other variables, x and z, are to be understood to be constants. And so that means that all of this and all of that, for the purposes of the calculation I'm doing here, I get to treat that as constants. And so this is not a monstrosity. This is just a constant times y squared, and that's easy. Right? So again, we're taking a y partial of y squared, again, times a constant, and so the constant just sticks around, right, as multiplicative constants do, and the partial with respect to y of y squared is just 2y. Everybody happy? So I nominate partial derivatives as being the easiest derivatives, single variable or multivariable, to compute, because it's just like taking a single variable derivative, except you get to just ignore a bunch of what you've written down. It's totally awesome. Okay. All right, a couple other quickie examples. Again, these look hard. They're actually easy. Again, you got to pay attention to the details. Here we're taking a partial with respect to x. So what I have here is not a function to the power of a function. I have a function to the power of a constant. That exponent there is just a constant. And so you treat it like any other constant. You bring it down and you subtract 1, and don't forget the chain rule, take the derivative of the inside, right? I mean, it's nothing to it. Second example, again, looks harder than it is. All of this down here is constant because it's a partial with respect to z. That means x and y we treat as constants. And when you have a constant to the power of a variable, that's just an exponential, and the derivatives at exponentials y'all probably remember from Calc 1. That's our let's see, what do we call that? Exponential chain rule, or generalized exponential rule, or I guess it's called different things in different books. Is that cool? Yes?
What's that little thingy?
The little what thingy?
In front of the x squared plus y squared.
Oh, right here. Oh, that is bad handwriting on my part. That is L N. And I was kind of writing in a sort of a half script, half print, and that's I'm sorry about that. Yeah. You'll get used to my handwriting eventually. Yeah. Okay. All right. So now here's a weird thing to consider. This is an important thing though when you're developing new mathematical ideas. And that is, while yes, you're allowed to define whatever you want, right? You can't make people care, right? So I can say I would like to hold most of the variables constant because that makes my life easy. And then everyone else in the room should be thinking, okay, weirdo, what do you do? What gives you okay, I guess you're allowed to do that, but how does this help me? Right? What does this mean? Does this mean anything, or are you making stuff up for no particular reason? Right? So I have made some stuff up here, and I have to persuade you that there is a good reason that I've done this. You can't just write stuff down and tell people it's important and expect them to believe you, right? Okay, so why is this important? Specifically, what's the geometric manifestation of this? What does this look like? Okay. First thing I have to hit, y'all are going to notice this point rearing its ugly head again and again in this course. What it looks like and how you interpret a mathematical object geometrically, it depends dramatically on what kind of a picture are you talking about. Are we talking about a graph? Or maybe we're looking at a level set of the function. Or maybe the function's a parameterization of something, right? I mean, the kind of picture is going to dramatically influence the corresponding interpretation. So heads up about this. This is a huge point. I can't tell you how many times I've seen on student exams that they take a calculus of graphs interpretation of a level set, and everything they've written down is garbage. Absolute nonsense, 100% wrong. So anyway, very, very careful, please. This is one of the unfortunately inconvenient things about doing multivariable. So you really got to pay attention to what is your picture, what kind of picture is it. So starting off, trying to make sense out of partial derivatives in a graph context, just to get the ball rolling. Okay, so we have here a function of two variables. Those two variables are x and y. You're going to, in this graph, kind of visualize the xy plane, kind of, sort of, if you will, as being the domain. And then notice we have one output variable. That output variable is z. Notice I'm setting the value of the function equal to z. That's, of course, what makes this a graph, right? And that output axis, if you will, kind of, sort of, I'm going to represent as the vertical axis there. So again, graphs are weird. They take the domain and the target, they kind of smash them together to make this sort of hybrid Frankenstein sort of space that you're putting together different things in the same thing. It's pretty weird if you really think about it. Okay. All right. So looking at this graph, looking at the resulting surface that you get from setting the output equal to a new variable. On that context, let's try to make sense out of what is a partial derivative with respect to y. What do y partials look like on this picture? Okay, good news. In some sense, we already know the answer because our process for writing down a derivative with a partial derivative, it's a two-step process, and each of those steps we already have existing interpretations for. So the first step in writing down a partial derivative, of course, is that we fix all the other variables. And if we're taking a partial with respect to y, that means we are fixing x. Okay, well, yeah, but we're starting at this point a comma b. If we're starting at a point where x is a, and if x isn't allowed to change, then that means x is stuck being a, which is the equation of this vertical plane, you'll notice perpendicular to the x-axis, So geometrically, the first step in our process is to take the appropriate vertical cross-section of our graph. And now I'll point out as another way to think about this is just a different point of view. Keep in mind we're taking the partial with respect to y. Notice that as we're taking the partial with respect to y, fixing x has us on the picture taking what you might call a cross-section in the y direction, kind of, as it were. Does that make sense? This is an opportunity for subtly confusing conflation. Make sure don't conflate the variable that defines which direction you're going with the variable that is being set equal to a constant. It's real easy to get those switched. So again, careful, heads up. Okay, second step in the process of computing a partial derivative is to take your resulting single variable function. You know what? Let me stay here for a second. Take your resulting single variable function and take its regular old, good old derivative. Okay, well, my resulting single variable function, keep in mind I've taken this cross-section of my surface. That cross-section is going to be a curve. Notice, I'm just saying, this curve gives height, namely z, as a function of y. X is fixed, right? We don't have to worry about x. But this height z is a function of horizontal movement y. So I have vertical as a function of horizontal. Morally speaking, this is a graph of my resulting single variable function. It's height as a function of width, as it were. So when you take a derivative, you get a slope, just like in single variable calculus. So the derivative with respect to y means we're just going to look at the slope of that tangent line, and that gives us this nice, convenient interpretation of partial derivative with respect to y. Partial derivative with respect to y is the slope of the tangent line. You're going to be tempted to just kind of stop there, because that's where in single variable calculus, we just say, partial derivative, slope of the tangent line. Right? Very importantly, though, we do need to specify that when I say slope of the tangent line, I mean slope of the tangent line as I go in the y direction. And furthermore, just as a reminder, and again, this issue is not an issue in single variable calculus. In single variable calculus, every picture is a graph, pretty much, right? Not so here. So we really should specify slope of the tangent line to the graph of the function. Again, this does not apply if you're looking at a level set of the function, or if the function is a parameterization or something like that. Okay. All right, so pretty straightforward two-step argument. Now, I have an exercise for y'all. I think this is a very healthy exercise, and that is to persuade yourself. Think it through, draw the pictures. Devil's in the details, be careful, right? But persuade yourself that the x partial is the slope of a tangent line in the x direction. Now, that's exactly what you would expect, right? If you were to just do a find and replace, replace all the y's with x's, this is what you get. That's not a mathematical argument, of course, right? So draw the pictures, think it through, be careful, and persuade yourself that this is what you get with the x partial. And again, to the graph. Good exercise. Okay. All righty. Now, reminder, all of this, and this is the interpretation that they push real hard in high school multivariable calculus classes. But all of this only applies if you're talking about the graph. And of course, your interpretation depends on what kind of picture you're looking at. So now we're ready to go if we need to interpret partials on a graph. But what if we're looking at a different kind of picture? How would I interpret partial derivative in one of these other kinds of pictures that we will spend a lot of time working with, right? So what do we do, for example, if we're looking at what I like to call the literal picture? So here's an example. We've got a function where the domain is R3, which I've literally drawn a picture of, and our target, let's say, is R1, which I have literally drawn a picture of. Right? And if we're thinking about the function that takes stuff out of the domain and into the target, which I'm literally doing as best I can, representing with that arrow there, right? Where's the partial derivative on this picture? Well, there's not much of a picture. I've already kind of confessed that, right? I mean, there's no shape, there's no surface, there's no curve, right? But I can, on this picture, very naturally talk about how things change. And keep in mind, the big idea of a partial derivative is that y is the only variable that's allowed to change. So if I'm talking about the partial with respect to y, I'm talking about moving exactly in the y direction. Notice that as I move exactly in the y direction, x doesn't change at all. X is fixed, and z doesn't change at all. Z is fixed. Yeah? So that's how my input change looks at, whoopsie, wrong color. That's how my input change looks in the picture. And then, of course, there is a corresponding output change, because as I move my input, my output will also move. I'm going to call that df. And if you want to know what is the interpretation in this context, given that this is the picture I'm looking at, how would I understand partial derivative? I would understand partial derivative like so. It's the thing that you multiply by your input change to get your output change. So it's a relationship between input changes and output changes. Right? Here we're just explicitly seeing these changes. You might say back here, when we're talking about slope, that it's rise over the run. Well, again, that's a fraction of output change divided by input change. Again, a kind of a relationship, right? Here it's, we're just thinking of it in a different way. Is everybody happy? Okay. What about level sets? Let me start with pointing out the big common mistake, the big mistake that a lot of students make. I see this all the time, and this is catastrophic. If I ask a student, what is the partial of f with respect to x, what does that look like? A lot of students, they look at this and they see, oh, it's a derivative. Derivatives are slopes. And they're just like, I guess it's the slope of that tangent line right there. Yeah, that's wildly wrong. It's got nothing to do with the right answer here, because that's not a graph. Right? Derivatives are slopes of graphs. They're not slopes of whatever picture you might happen to be looking at. It just doesn't work. Right? So don't step on that landmine. Don't make that it's a very common mistake. It's a very easy mistake. Again, it's at this point the student's responsibility to always think about, okay, what kind of a picture am I looking at, and then to interpret calculus concepts accordingly. Okay, so in this context, here I have some various level sets drawn. And reminder, level sets, I mean, my favorite metaphor for level sets is contour lines on a topographical map of like a hilly, mountainous kind of area, right? And so whenever I'm thinking about stuff like this, I'm thinking, okay, how does this hike look, right? And so if I ask a partial of f with respect to x, that suggests, let me zoom in here. Okay, so each one of these lines represents a certain number of feet of altitude. So maybe that's 300 feet of altitude, and this, maybe that represents 400 feet of altitude. So partial with respect to x says how fast is the function increasing as I go this way, and notice as I go that way, oh my gosh, I've got to gain 100 feet of altitude over a very short distance. That sounds steep, right? That's going to be a steep hike. I would expect the partial derivative to be large because it's steep. Does that make sense? Okay. So, as expected, partial of f with respect to x, partial of f with respect to x is large. Okay, now, let's ask what about the partial derivative with respect to y? Okay, partial with respect to y means I'm moving in the y direction. As I go that way, okay, I'm going to still eventually make it to this other contour line, but thankfully I get to cover that same amount of altitude gain over a much greater distance. That spreads out the altitude gain. That looks like a much gentler slope, right? That looks nowhere near as steep. I'm thinking that partial derivative is probably a lot less. And as we might expect, the y partial is relatively small. Does that make sense? Yep.
Can you determine the sign from this?
No. Sadly, the way I've got these drawn, that's one of the problems with understanding a function by way of level sets. Unless you label the level sets, and by the way, of course, a lot of topographical maps will, and they'll very commonly do stuff like they'll label, that this is 100, and then this is 200, and then the 300. Etc. And if you do stuff like that, then you can, I think I get some sense for which way I'm going. But without those labels, no, you can't. And another thing that you notice is conspicuously missing here is I don't have any sort of a legend indicating what horizontal distances are, right? So how far is this supposed to be, right? That distance, between that point and that point, is that 10 miles or is that 20 feet, right? And so that's also missing from this picture and very often. But so you're getting a sense of magnitude and plus or minus, as you point out, is a hard thing to get depending on how the level sets are drawn. Yeah, that's a great question. Okay, cool. Okay, so just to hit it all again, we've said all these things, but notice a very different interpretation of the partial derivative in the context of level sets. Very different interpretation in the context of this literal picture. Very different interpretation in the context of graphs. Y'all have to constantly be heads up to what kind of a picture of my function am I looking at, and then interpret the calculus accordingly. Okay, here's a related idea. This idea of a linear approximation. This is the first step in a long discussion. It's going to be important. And I'm pretty sure you all remember linear approximations in single variable calculus. You probably remember this function right here. Right? Does that ring bells? I hope. Right? So why are we interested in this function? And there's different points of view you can give. I'm going to push a particular point of view that what I like about this function is this is the unique degree 1 polynomial that I'm going to say mimics my function f in terms of value and derivative. So it's got the same value as my function f at the point A. And it also has the same derivative as my function f at the point A. So at the point A, this function I'm calling L, this thing that y'all remember and that I'm written down here, my take here in this context, my take on why we care about that is it's the best mimic of the function f at the point A. Okay. All right. So that said, here's a multivariable version of that. you have some multivariable function, several inputs. Now, real quick, you're going to notice, by the way, we're starting off looking only at a single output value, aka we're looking at a real valued function. Just to get started, we'll talk about vector valued in a few minutes. Just to get the ball rolling, real valued. Multivariable function, several input variables. Y'all can check for yourselves, and this is a really healthy exercise. This function right here is the best mimic of f at the point A, in the sense that it's got the same value as f at the point A. And it's got not only the same first partial, but all of the first partials, I should say, with respect to all of the input variables, all agree with f at the point A. And again, I think this is a really healthy exercise for you all to confirm this for yourself. You don't need to do this in any sort of generality. If you want to make n equal to 3, for example, just because if you can see this for n equals 3, you'll see the pattern. You're good, right? That's fine. But really healthy exercise, and I hope you'll do that. Just a quick comment as to how you're going to do that. I would encourage you first to remind yourself how this works. How do you confirm that L agrees with F in value and derivative at the point A for the single variable? And in particular, all you got to do is just plug and chug. There's really not much to it, right? And do keep in mind that this, because it's evaluated at the point A, because A doesn't move, right now X does. X is the variable. But A doesn't move. A is a constant. That means that f prime of A is a constant. And then as you compute L prime, think about how that factors in and everything works out, and we win. Likewise, along those same lines, this thing right here is evaluated at the point A. By the way, that's what that notation means. This vertical sort of bar with an A at the bottom. This means I'm evaluating the expression to the left at the point A. And that also is a constant, as is this also constant. So keeping that in mind, this is just a matter of plug and chug to confirm these equations. But again, healthy exercise. Everybody should do this. Take you a couple of minutes. Just want to make sure you see exactly how that's working out. Okay. So this is, by the way, an important formula to make sure you remember, which I will recognize is a lot of width. Right? There's a lot of characters on the page there, and that's a little annoying, but you're going to notice that there's a pattern. You're going to notice, for example, that all these terms kind of look alike. You're also going to notice that in all of those terms, the first factors all kind of look alike. And you're also going to notice that in all of these terms, all of the second factors kind of look alike. And that might lead you to notice that if we look just at what you might call the sort of the last terms there, all of these last terms I can rewrite as a dot product. If you think about it, that's what a dot product is. A dot product is a sum of products. As we just recognized, what I have up here in green is a sum of products. It's straight up a dot product. In fact, you'll notice very quickly that all of these, wrong color, all of these orange factors here are just the various coordinates of the geometrically natural vector x minus a. Those are literally its coordinates. So all of this together strongly suggests that we should look at all the, let me just get rid of all this, that we should look at all these other factors, all of these partial derivatives, and call them coordinates of a single vector. We're going to use this notation right here. We take all these partial derivatives and just kind of assemble them together, right? And that makes these the coordinates evaluated at A, of course. But all of this together is what we call the gradient of f. And that's just a notational choice. In this context of our development of ideas, I'm choosing to do that just because it makes it more convenient to write down the linear approximation. And in particular, all of this great big, lots of stuff, much more compactly written down like this. Is everybody with me? Okay. So, some of y'all, depending on your background, you may have heard of the gradient of a function previously. If you have, cool. There is many more things to say about gradients, and we will later on in the appropriate, when we get to that point, right? For the moment, I want you all to think of a gradient as just being a notational convenience. That's it, right? We don't know geometrically what this means. It's just a way of keeping me from having to write down a lot of expressions like that up there. Okay. Okay, so with all that in mind, let's do one. Let's find the linear approximation of this function right there. Now, that if you want to do a linear approximation, we have to decide at what point are we doing the approximation. So I'm going to say 1, 2. That's our A. So that's going to go sort of there and there. And how do you compute this approximation? Well, it's really just plug and chug. I'm going to need to take the point A. I'm going to need to plug it in to my function f. Right? And the value that I get when I plug that point into that function is 5. Plug and chug. Nothing happened there. Okay. All right. Next term, I'm going to need to compute the gradient. All right. So there's a fair amount of effort that's going to go into computing this gradient. First of all, remember that gradient is all the various partials. So I compute the various partials. Right now, we've just talked about partials. So y'all are, of course, going to rehearse the process of how to compute partials. And I'm just going to wave my hands at this here, but that expression x squared plus y squared, the partial with respect to x is 2x, the partial with respect to y is 2y. You want to make sure to think that through, make sure you're clear on what happened to the other term, right? The function has 2 terms, these partials only have 1. Why is that? Something you want to make sure you think through, right? So make sure you can compute those. Then again, of course, we need to evaluate at the point A, and so I need to plug in the point A and see what we get and the values that we the values that we get when we plug in are 2 and 4, and that goes there. Very plug and chug, yes.
So the 2 goes to 4 because it's like x and then y.
Yeah. That's right. So that's right. When you're talking about a gradient, you do have to have a firm decision made on what order the variables go in. Yeah. So you can't just choose to reorganize your variables. So here I'm putting x1 and then x2 and then x3. Or in this example, I guess it's x first and then y. Oh, you can even see that right here. See, I've explicitly indicated that x goes first and y goes second. Yeah. Is that cool?
Yeah.
Yeah. Cool. All right. Okay, the last little bit here, the x minus a part, is actually the sort of the easy part. X minus a, I claim, turns into this because x is just xy, and a, as previously discussed, is 1, 2. So that's just a matter of writing it down. And there you go. Here's your linear approximation. Everybody happy? Okay. All right. Now, some people would tell you that you really should then multiply all this out and get an answer that is as compact as possible. And sometimes that even makes sense. In other cases, it's not clear what the benefit is for that. Now, I'll confess that if I were going to be using this linear approximation, and if I was going to be computing the values of the linear approximation with a computer that was going to have to do this several billion times, and I wanted to be as fast as possible, something like that, then yeah, sure, streamline it. Yeah, sure, right, fine, right. But there's a case to be made that other than some case like that, there's something actually really nice about this form right here, because I can see the structure, right? I can see where each of these elements came from, right? And I think a pretty good case could be made, unless you have reason to multiply it out. What's the point? Just go ahead and leave it like this. Everything's in there. This is not an Algebra 1 class. I don't need to know that y'all can, anyway. I'm going to, most of the time, just leave it like this. Okay. All right. Okay, now let's get to the vector-valued case, as previously discussed. So vector-valued, right? Several output variables now. And you're going to know, well, it's still multivariable, still several input variables, now several output variables. What I did with the real valued case is I wrote down an answer and then subsequently gave you the notational convenience. If I do that for this next example, it's going to be just horrendously inconvenient notation. And so I'm going to spare all of us and just go straight to the notational convenience, right? It's morally equivalent to what you're seeing here. You could multiply the whole thing out, but let's just, again, be kind to ourselves. Here's the notational convenience. Again, this is just the sort of bookkeeping convenient choice to make. So it's going to come seemingly out of nowhere. Here's the thing. This is called DF. There's a good reason we're going to call it DF. I'm going to do my best to not slip up and actually reveal that reason until it's well motivated. But anyway, so we're just going to call it DF. You'll notice it's a matrix. You'll also notice that it's a matrix where all of the entries in the matrix are partial derivatives. Okay. Which, by the way, kind of like the gradient, right? In the gradient, all of the entries in the gradient vector are partial derivatives. Okay. Okay. I can't get that. There we go. Okay. Now, there is something very important about the structure. You can't just take all your partial derivatives and toss them in there like a box you're about to put in the attic, right? The order matters. These have to be assembled in a particular order. In particular, all of the partials with respect to x1 go in the first column. Whatever your first variable is, all those partials go in the first column. Likewise, second variable, second column, third variable, third column, and all the way on down, partials with respect to the nth variable go in the nth column. Okay, so loosely speaking, what I like to, the loose phrasing I like to give for this is that this is the x1 column, et cetera, and this is the xn column. Okay. That said, now notice in the first row, we're talking always about partials of the first output coordinate with respect to different input variables, right? But all those partials in the first row are partials of the first output coordinate f1. Second row, partials of f2, et cetera, et cetera. The last row, you'll notice, are all partials of fm. So likewise, I'll refer to the f1 row and the f2 row, et cetera, all the way down to the fm row. Is everybody on board? The most common mistake that I see students make on this is they accidentally get rows and columns conflated, and they talk about the X1 row, which doesn't make any sense, right? That's very importantly not the structure here, right? That it's not good enough to be organized in a sense. It has to be organized in the right sense, and this is specifically and exactly how we have to do it. So make sure to get that straight. Columns correspond to input variables. Rows correspond to output variables. Okay. All righty. And with that said, here's the happy little answer. Here's what our linear approximation looks like for a vector-valued multivariable function. And I claim, and again, I'm going to leave y'all to confirm this for yourselves. It's a good, healthy exercise. This has the same value as f at the point A, and this function has all of the same partial derivatives. For all of the output coordinates, with respect to all of the input coordinates, this function has all the same partial derivatives as f. Okay, good exercise. And just real quick, I'll point out that when I say I want you all to confirm all of this, let's say just because you don't need to do this in general, so just for notational kind of convenience, maybe do this for like n equals 3 and maybe m equals 2 or something like that. That'd be a reasonable choice. All right. Okay. Again, let's see an example. Here we go. This example here, notice vector valued, right, because there's 3 coordinates. Vector valued multivariable, because there's 2 input variables. Vector valued multivariable function, and we want to find the linear approximation at this point 1, 2. So we're going to follow the rules, and you'll recognize here's our general structure. That's just copied from above. I'm just going to go through this one little bit at a time. We're going to take A. We're going to plug it into our function, right? The function f at the point A, and that means that this term turns into that. Now, again, make sure you can do that, right? That's just arithmetic, but think it through. Okay. Now we're going to need to know df. We're going to need to know various partials. So we're going to take our function. We're going to take all the appropriate partials. Anyway, we're going to take all the appropriate partials. Now there's detail devils in there. Real easy to mess this up. Real common mistake. A lot of students make the mistake of saying, oh, well, I kind of see these written horizontally, at least on the page. It kind of looks horizontally, and they forget that, but those are all different input variables, right? So each one of those corresponds to a row, not a column, right? So the partials of that go here, and the partials of that go here, and the partials of that go here. Don't accidentally transpose it. Again, it's really easy to mess that up. Really easy to mess that up. Okay. If it helps, and everybody's different, but if it might help conceivably, remember that a comma means new line. Right? So typographically, sure, I guess I wrote this horizontally, but the commas are actually an indication that this is a vertical list. Right? So this is a vertical vector. It's a column vector because of the commas. Okay. All right. So what we have here then, this first column, this is all of the x partials. Right? You take the x partials, you get those, right? And likewise, these are all the y partials. So y partial, y partial. Okay, so make sure to get that right. Now, of course, our factor here is df evaluated at the point A. So yeah, I've computed df, but now I've got to plug in the point A. So this has got to sort of plug into there, and then the resulting actual df, the evaluated df, is this, which then goes there. Yeah? All good? Okay. All right. And then x minus a, right? So x and, let's see here, minus a. Okay. All right, so it's all very plug and chug. That's nice. Okay, now a couple of really quick observations. Punchline is not only are all of the elements in the first column individually partials with respect to x1, I make the observation that the column itself is the partial of the entire vector valued function f with respect to x1. So in other words, if you look at this, and if you were to ask, okay, what would be the partial derivative of the vector valued function f with respect to x1, well, in fact, you would get exactly that list of coordinates, and it would be exactly that vector. So that's just a quickie observation. The less obvious observation, but very much worth noting, is that the rows are gradient vectors. And again, you just kind of have to look at the formula to see that, sure enough, it actually is. So here we go. Let's look at this row right here, this first row, and I see that I'm taking all the partials of f1, specifically all the partials of f1 with respect to all of its input variables. Oh my gosh, that's exactly the definition of a gradient. A gradient is the partials of whatever function with respect to all of its different input variables. So how about that, right? So neat coincidence there as well. So the columns are natural, and the rows also are natural. Okay, another little quickie observation here, and so this is a little bit of a flashback to single variable calculus. Before I get to the multivariable version, let me just remind you of the single variable version. I know y'all have seen all this before, but again, I want to make sure we get this done right. The conflating importantly different things is a problem, right? And what happens very often is students conflate a tangent line with a linear approximation. And in a lot of single variable calculus classes, they just talk about them interchangeably as if they're literally the same thing. And they're not. Now, the problem, right, is that one is the graph of the other. Okay? And I've already observed in single variable calculus classes, they just, every picture you ever see is a graph, and so we very often just conflate a function with the curve that is its graph. And in single variable calculus, you can kind of get away with that. You'll never get stung on that because you'll never see a picture that isn't a graph. But it's certainly not going to be the case here, and so we do have to be really, really clear about the distinction. So this thing right here, that's our linear approximation we've been talking about. That is a function. It is an algebraic thing, not to be conflated and confused with its graph. The graph is what you get when you set that equal to a new variable, in this case y, thus giving you this equation, and that is the equation of the tangent line, which is a geometric object. The linear approximation is a function, it's an algebraic object. The graph is the tangent line, it's a geometric object. Everybody see the difference there? I know it's fussy, but it really matters. Okay, so same deal when we're talking about the multivariable case. Now here you'll notice I have a function of two variables, and here's the linear approximation. Right, function of two variables. Note the picture. Okay. Looking at a graph. If we take the wrong color. If we take the graph of that linear approximation, then the result is this equation, which is the equation of a plane, and that is what we call, no surprise, the tangent plane for a multivariable function. Graph of a multivariable function. How we doing? Everybody buy it? Okay, so heads up, please do be very careful to distinguish the function that is the linear approximation from the plane that is its graph that we call the tangent plane. Okay. All right. Now we get to a subtle business that I wish we had more time to talk about, and we just don't. So I'm going to be super fast with this. I'm going to get through 2 pages in the next 7 minutes, and it's just not. Again, it's not quite what this course is about. But there's some beautiful mathematics in here that I'm about to just kind of gloss over and kind of wave my hands at real quickly. Powerful and important and beautiful mathematics that isn't the point of this course. Okay, so notice I deliberately glossed over a few minutes ago this point right here. I say, if the linear approximation exists, then it would be blah, blah, blah. So why do I say if it exists? And because the motivation that I give for why do we write down this formula is because that thing behaves in a way that I like, right? Well, if it exists, it does, right? Roughly speaking, what we have here is a sort of a process of elimination. I'm looking at all of the degree 1 polynomials, and I'm just trying to decide which of these degree 1 polynomials do I like the best, right? But what if none of them were any good in the first place? Well, then writing down a formula isn't helpful. So everything that I did here previously is on the assumption that there even is something that could reasonably be called a linear approximation. So now let's look at this example here, and I claim sometimes there really isn't a good linear approximation. I'm going to start off with this function right here, and it's a wacky function, and fair, it's legal, perfectly legal. There's nothing wrong with this function. Perfectly fine as a function. This function for whenever either of your input variables is 0, then the value of this function is 1. And everywhere else, the value of the function is 0. It's a hard picture to draw, but anyway. It kind of looks like one of those little, I don't know, have y'all ever seen somebody do a mannequin, right? They have this little cross and the strings come down and they do like this and then the mannequin dances and stuff, right? So this is kind of like that. Anyway, so that is the graph of a perfectly reasonable function. And tragically, at the origin, this function is perfectly well defined and gives no indication that we have a nasty function here. And the partial derivative with respect to x is perfectly well defined at the origin. The values of the function as I start at the origin and move in the x direction, they're all 1. They're all constant. And so this partial derivative is no problem, 0. And in the y direction, again, no problem, at the origin as I move in the y direction. Constant, and that partial derivative is 0. And so you'd be tempted to say, okay, well, I can just plug in these perfectly acceptable values into our linear approximation formula, and the resulting linear approximation that you would conclude, seemingly, I'm going to say naively, is that the function 1 would be a good linear approximation for this entire function, and of course that's ridiculous. This is a horrible linear approximation. This is unforgivably terrible, right? Because, for example, as I move toward the origin, let's say in this direction, the value of the function is 0 the whole way along, but the value of my linear approximation is 1. Why am I putting check marks? Those are bad. I'm getting values of 1 all the way over. The function has values that are 0 all the way over. That is a poor attempt at a linear approximation. But it totally follows our formula. So our formula was naive. Our formula was making assumptions. So now, how are we going to fix this? Well, it's a nasty business. Roughly speaking, I want to make sure everyone's aware of why it's not good enough to simply require that error go away. A lot of people think you can just, the error is bad, and if the bad goes away, then doesn't that just leave good, right? That's kind of the naive sort of attempt. But check out how silly that is. If I want to do a linear approximation of this function, is this a good linear approximation? No, come on, get out of town. That's ridiculous. Look at that. That's not even going the right direction. And yet, the error, how far I am off, is approaching 0. Okay, so vanishing error, not gonna cut it, not good enough. So we're going to consider this different idea called relative error. Relative error says how far off are you in the output, and then divide by how far away were you in the input. And with that in mind, now let's look at relative error, and you can see our errors do approach 0. But that's just the numerator. We're dividing now by our, how far away are you in the domain? And the relative error, not 0. So the fact that this relative error is not 0 is what allows me, with confidence, to be able to say, you know what? I don't like that poor attempt at a linear approximation. Obviously wrong, right? That function right there is clearly not a good approximation of this function that I started with right there. Relative error, not going away, is a way to detect that. So you're going to find in the book a formula that looks kind of like this. And okay, let me just wrap this up real quick. We need to look at this expression right here, and all this nightmarishly complex looking thing is nothing more than the relative error. It just says, and you can see it right here, we're looking at the value of the function, and then we're subtracting, and let me group these together just for sort of convenience. We're subtracting then our linear approximation. This is just error divided by displacement in the domain. It's just relative error. So now it remains that this definition of what does it mean to have a good linear approximation. What is, and by the way, the equivalent way to say this, the function is differentiable. Yeah, it's a clunky, nasty expression to have to look at and deal with and look at the limit as x approaches a. In practice, we're not going to actually use this at all. But I wanted you all to see that this actually kind of sort of makes sense in a way, and that all it is just the assertion of vanishing relative error. It's the assertion that that's why this is a bad one, as opposed to not being able to see anything wrong with it from this naive point of view here. Okay, we'll call it a day right there, and a couple of notational points y'all can read. Y'all have a good one. We'll pick up here on tomorrow, I'm sure. This isn't Friday, so see you tomorrow. And again, reminder, apologies, but I have to run immediately here.